Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Deanna Hooper, Charlie to friends, and I'm a theoretical physicist currently working as a university researcher over in the Helsinki Institute of Physics in Helsinki, Finland. And I'm a cosmologist, which means that I study the universe, the contents of the universe, how things evolve, how things interact. I love being a cosmologist. It's a super fun topic. I get to study space. It's cool. And I love chatting to everybody about all of the cool things I get to work on. So for anyone who doesn't yet know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about space, about physics, about academia, about cosmology, about Finland, about my currently zoomy cats, and I will do my best to answer your questions. As always, I might not have all of the answers, but I will tell you if I don't know something and we can try to figure it out together, or I just save it for a future stream. For anyone who's a first-time viewer, welcome. For the regulars, welcome back. I see we already have some of the regulars here. Ben, Brath, Paul, great to see you. Scott, you can't stay. That's okay. Thank you for stopping by to say hi. David Howden, James, Lasargo, great to see all of the regulars coming in, as always. You know, it's Cup of Cosmology has been going on for 10 years now, and there are some of you that have been here since the very early days. And I'm still always surprised to see that so many of you come in week after week. It is great to have you all here. If you haven't done so yet, if you're new here, or if you've just forgot to do it in the past, please do subscribe to the channel. It really does help. Like the video, leave a comment, share the stream, whatever you want to do. It really does help boost the algorithms. And then boosting the algorithm is great because then I get more viewers, which means I get to talk to more people about the cool stuff that I get to work on. Also, if you're on Twitch, there's also buttons you can press over on Twitch. You know, just press buttons, make stuff happen. It's very cool. Speaking of pressing buttons, I have a new button here in Restream that has a big red icon. And okay, that's not a button I want to press. Okay. As always, you'll know I'm going to get sidetracked and distracted. That is the nature of the stream. So, Cup of Cosmology interactive stream. The idea is you can all ask whatever you want, and then I will do my best to try to answer the questions, which means that the direction of the stream is entirely up to you. You get to decide what we talk about based on the questions you ask. If you don't ask questions, I get to ramble about my favorite things, which will be a random mix of stuff, probably involving the beach ball behind me, or, you know, gravitational waves, stuff like that. So please do feel free to ask any of your questions, and I will do my best to answer your questions. Also, I'm aware that I came on like 1 minute late. The reason for that is just as I was about to click the go live button, one of my cats screamed from the bedroom. And he does that when he wants attention, but he screams in a specific way that sounds like he's in pain because he's figured out that that gets my attention. So, of course, before clicking the go live button, I had to go check on him, and he just wanted to play. So now my cats are playing together. But yes, that is why I was a few seconds late today. Not that you'll notice, but just if you did, blame the cats who are now staring at me because they don't like being blamed for things, even when it's their fault. Okay, big red icon that says don't press me. It doesn't say don't press me. There's just a big red icon. And if I put my cursor over it, it says do not press while live. I'm like, well, why are you even there? What is the purpose of that button if I'm not allowed to press it? Why does it have a red icon on it? I guess it has a red icon to tell me not to press it. But who doesn't want to press a big red button? If there's a big red button, you must press said big red button. Fun question. Fun tangent, even. Fun tangent. When I lived in Germany, in Germany, there was kind of a hobby shop that had like small trains and stuff and a lot of very cool stuff. And they had a big horn on one of the walls, just a big horn, like one of the ones that you could squeeze and it would make a loud noise. And there was a post-it attached to it just saying, do not. I'm like, but it's there. If it's there, it needs to be pressed. That's how these things work. I did not press it because the shop assistants were very keen on making sure nobody pressed that button. Anyway, give me a big red button. I will absolutely press it. Back to the chat, or to the chats. Let's go. As you all might notice, I'm kind of hyper today. You know, it goes in the territory. What would Cup of Cosmology be if I wasn't hyper? You say my cats have zoomies. Maybe I do too. I'm not even that caffeinated today. I'm just hyper. Okay. Comment from Perth. Have I told you I read your Mastodon username as DTuper instead of DC Hooper? Happens to the best of us, don't worry. Happens all the time. I use both initials in pretty much all everywhere. And then yeah, people have called me Cooper somehow. The H gets dropped, whatever, you know. I won't take it personally if you misread my username. But yes, DC Hooper, that is where you can find me basically on all socials and my webpage. My webpage is dchooper.com. Easy to remember. Okay, press the button at the end of the stream cannot do any harm then. Exactly, right? It's there to be pressed. That's the thing. Okay, question here from Ottaz. My question, how are you? Thank you for asking. I am good. I am good. I know I hesitated with my answer. I am good. It's been a kind of intense week. I had a lot going on this week. But when don't I? But I had a very good weekend. I was supposed to rest yesterday. I did not rest, but I mostly rested today, somewhat rested. So I am doing well. Thank you for asking. I know a Cup of Cosmology was not online last week. That was intentional because I had some other stuff going on last weekend. And next weekend, Cup of Cosmology will definitely be online. Then in March, I might need to take a couple breaks because I think I've overbooked myself in March, but that's a March me problem. But thank you for asking, Taz. I'm doing well. I am doing well. I'm happy to be on Cup of Cosmology, and I had a lot of good food today, so I'm doing well. Okay. Comment from Paul, and then I will read the question about massless particles. Comment here from Paul. Here in the US, in the big old USA. Hello, baby. I'm not sure if you guys can hear, but my cat is making that noise from the bedroom again. That sounds like he's in pain. He's not. He just wants attention. I'm not sure if the microphone is picking up on that, but I have a cat screaming at me from the bedroom and another one right here on the desk with me. Hello, do you want to come say hi? Well, you briefly saw a cat. Okay, here in the USA, we're entering silly season for the midterm election cycle. They're raising all kind of rumors about alien life here on Earth. When aren't they using a smokescreen? You know, at this point, it's one smokescreen after another to distract from all the bad stuff they're doing, but yeah, good luck to all of you in the US and in other countries. It's not like it's much better in other countries, depending on the country. Okay. Question from David Howden. Can massless particles travel slower than light speed? Absolutely. So we have this general idea that there are different velocities in the universe. Different particles can travel at different speeds or at different velocities. But there is an upper limit. There is an upper limit, which is the speed of light. Nothing in the universe can travel faster than light in a vacuum. And it's important that we mention here in a vacuum. So in a vacuum, which is basically most of space where there's nothing, light is the fastest thing that travels. Nothing can travel faster than light. We also know that some particles have mass and some particles don't have mass. For an example, particles that make up all of known visible matter, like, electrons and protons and neutrons, these are not technically particles. Yeah, let's call them particles. They're not subatomic particles, but let's call them particles. Protons, neutrons are made up of quarks. So your quarks, your electrons, all of these have mass, and these therefore cannot travel at the speed of light because you would need an infinite amount of energy to accelerate a massive particle to travel at the speed of light. It gets to the point where it just cannot accelerate faster. So massive particles can never travel at the speed of light. So then we can ask the question, what about massless particles? Can massless particles travel at anything other than the speed of light? And the answer is yes. So particles without mass, like photons, which are particles of light, can travel at the speed of light, as photons do, because they are photons, they are particles of light, they travel at the speed of light. However, it is important to mention again that this is in a vacuum. You can slow down these particles. For an example, if you want to slow down a photon, the best way to do it is to put lead. Put a brick wall or a lead wall, and the photons will not be able to go through. They try, but they can't. They get slowed down. If you have any medium, anything that is not a vacuum, you can slow down light. For an example, if you have water, you can slow down light. If you have any liquid, you will slow down light. Any medium, even through air, light will travel a bit slower than it does in a vacuum. So even though massless particles can travel at the speed of light, they don't have to. They can be slowed down. This is something that you can confirm very easily yourself. If you've ever gone underwater, or like put yourself so you're half underwater, half over water, where you can see both, like one eye each if you want to get fancy, you will notice that there's a slight distortion. It's like images shift slightly. It's like something gets bigger or looks a bit distorted. And the reason for that is actually because the speed at which light is traveling changes when it goes from the air to the water. So when you hit the water, the light slows down very slightly, and that means there's a refraction index, which just means the light is diverted slightly. So that's what gives you the distortion or the changing in appearance when you look at something through air versus through water. If I put a pen, can we do this? Let's see if this works. Haha, yes, it works. Okay, got my trusty pen and my trusty water bottle. As you can see, when you look at the pen, let me put it behind with a black surface. If you look where the pen is outside of the bottle and behind the bottle, you can see that inside the bottle, behind the bottle, it looks like it's slightly lower down. This is, of course, the pen is straight. I'm not breaking the pen. As you can see, when it goes behind the water, it just moves very slightly. Now, of course, here we have a slight lens effect because of the plastic, but the main thing at play here is the water has a different refraction index or a different speed. So the light traveling through the air and through the water travels slower at different speeds, and then you get this kind of visual distortion. So I love when I can use it. This pen I've used this pen for so many visual explanations. It's a great pen. It's a perfect pen. It's my branded. Oh, that's not going to show up. It's my University of Helsinki pen. It just says University of Helsinki with the flame, which is the logo of my university. Okay, so yes, particles, massless particles, can be slowed down. They don't always travel at the speed of light. Clearest example is light moving through other things that are not air, for example, water, and slowing down. Follow up to this. I see there's a part 2 from James's question. Was there a part 1? I did not see part 1, James. I see part 2, but I don't see part 1 anywhere. So not sure where your part 1 went there. Oh, no, it says 2 parts. Okay, now I found both parts. Sorry, I didn't read. Sticking with the photons, there are two one related question here from David Howden. So the photons themselves are slowed down. Someone suggested to me that they are being absorbed and re-emitted. So although light slows, the photons themselves always move at c between absorptions. Is that completely correct? Let me think about that. So in some mediums, it is true that the light is absorbed and re-emitted. This is something that, yes, this is one way that it can happen, that the photons will still travel at the speed of light, but they will be absorbed and re-emitted, absorbed and re-emitted. But is that always the case as why photons slow down? I'm going to say no, but I'm trying to justify my answer in my brain, and I cannot justify it cohesively. Yeah, see, I feel like there's this kind of drag effect of when you're in a medium, you have a kind of slowing down of the particles because of the inherence of the medium. I do not think it is always because the particle is being absorbed and re-emitted. I think it is because of the energy needed to move the particle becomes more because of the resistance, which, now that I'm thinking about it, isn't a convincing answer. So I would say that the photons do slow down regardless of being absorbed or emitted, because they don't always interact with the medium that they're traveling through, but they can still slow down. So yes, I will argue that photons do slow down regardless of whether they're absorbed and re-emitted, but also please don't quote me on that. And that is the first thing I'm going to check after this stream now, because they should. Okay, I'm making a note of this because now I'm not sure, because as you say, David, this does sound like a convincing answer of, oh, they're absorbed and re-emitted. That sounds very plausible. I don't think it's true, but it sounds plausible. So I'm going to double check that. That is a very cool question. What is the exact mechanism by which photons slow down in a medium? That is something worth checking. Thank you. Excellent question, David. But back in the days when I was still doing the TTK live stream, so in Aachen, we had the Institute for Theoretical Particle Physics and Cosmology. I used to be able to do that in German as well. Institut für Theoretische Physik und für Teilchenphysik und Cosmologie, I believe it was. Anyway, back when I was in the institute with a very long name, and we were doing the weekly live streams with the institute people, I remember we did a whole stream about what it means to have mass and the definition of mass in photons and how that affects the speed at which they travel. It was a very fun stream, but it was super technical. And I think the recording of that one has unfortunately been lost. But we should absolutely do that again at some point, maybe in a slightly less technical way. Okay, sticking with this, there are more thoughts here. Yes, I'll get to James's question in a minute. But still sticking with this, there is a follow-up here from Prath. If they were being absorbed and re-emitted, it would be next to impossible for them to move in a straight line, as they would be re-emitted in random directions. Thank you, Prath. That is exactly the answer I was looking for. Yes. Yes. And follow up by Paul here. I think it sounds plausible because in water, between molecules, the photon sees a vacuum, but then slows down where it encounters each molecule. Well, we can consider the water to be a fluid at that point, even though there is technically separation between the molecules. There isn't really a big separation between the water molecules. It behaves as what we call an ideal fluid. So I'm going to go with what Pratt said here, that yes, if they were being absorbed and re-emitted, they would do so in any random direction and not in a straight line. And even though there is some distortion here, we can still see the pen in the background. We can still see that it has its specific structure. If all of the photons were being emitted and absorbed by the water, they would be absorbed and re-emitted in random directions, and you would not get the same clean image that we get. So I'm going to use that. Thank you, Brett. That was a very valid point to make. Also, thank you, Paul, for the follow-up as well. So even though it sounds plausible, I'm going to still go with my answer of no, photons are not always absorbed and re-emitted. That is not what causes them to slow down. What causes them to slow down is energy, mass, weird physics. You'll love my technical answers to these questions. Physics. But yes, they do indeed slow down. And yes, of course they slow down. Even when traveling throughout the universe, depends on their energy. Yes. Okay, photons can slow down. Okay, we agree with that. Right, there were some more questions that I wanted to answer. Let me just glance through this. We have the two-part question from James. Then we had another question. And I'm gonna answer Ben's question first, and then I'm gonna go to James's two-part question. But first, question from Ben, which we can answer quite quickly. What does the old term ether mean in physics? Does it still exist today? Great question. I love this. So ether is something that came up, I believe, first with Plato, when old philosophers were trying to describe the universe. I've said this before, and I'll say it again. I think it's a very valid point to make, that today we say cosmology. In the past, the people who did cosmology were philosophers. Philosophers were some of the first to have ideas on what the universe was made of, or what is happening up there. I used to, there was different cosmogonies, different Genesis stories, even going further back than philosophers. Every civilization at some point has had a creation myth or something to explain the cosmos, because it is something that inherently attracts every person at some point. So the ether was an idea of kind of it's not a term we use today, but it was supposed to be this kind of energy that is everywhere and that permeates the universe. Different interpretations of the ether will either tell you that it's what today we call space-time, it's what today we call dark energy. It is not a direct one-to-one relationship there, but the ether was kind of the cosmos, the everything, the empty space was the ether. So it's this kind of idea of stuff in the universe that had a specific energy. It is not a term that we still use today, although there are some parallels that people draw between what used to be called the ether. Today, you could reinterpret that as maybe being space-time. You could maybe reinterpret that as being dark energy, which is this weird type of energy that is everywhere in the universe, pushing the universe outwards, and that's pretty much everything we know about dark energy. So there are different explanations you can give today for ether, but none of them completely align with the original definition provided, I believe, by Plato within the context of the Platonic solids. Was it Plato who first talked about the ether? I cannot be slipping on my philosophy now. I love philosophy so much. I cannot be slipping on which philosopher came up with the ether. I'm fact checking myself on this because I need to think about who came up with that first. And of course, you look for ether and you get some random AI generated answer that is absolutely not what I'm looking for. Yes, ether was the fifth element of Plato in the Platonic solids. So he had the 5 elements. Well, he had the 4-element system, and his fifth one was kind of the divine air, so to speak. I'm so glad it was Plato. I had to fact check myself there because I cannot mess up my Greek philosophers. Otto, do not get in the trash room. And he's in the trash room. That is one of my cats who has still not calmed down. The other one has gone to sleep. But no, do not try to climb the door. They do when they know I can't go and stop them. Anyway, Nina, great to see you. Thank you for popping by. Always nice to see you in the chat as well. Yes, so ether, Plato. It was this idea of the divine air, the everything that fills space. It's not something we use today, although with a slightly different spelling, it's referred to a specific type of chemical compound. If you drop the A from it, just ether, ether, that is a chemistry thing today. But the ether, how Plato originally intended it with an A thrown in the mix, is not something that we use today, but it was something that was a step towards getting us to where we are today. So, every step along the process has helped us to get where we are today. So great question. Short answer is no, we don't use ether anymore, but it is something that has historical value in terms of when you're studying like the philosophy of science or the history of science, ether is an important step along the way. Okay. Then there was the two-part question from James, which looks interesting, and I'm going to answer it. Let me read the question first. If the Big Bang is a result of an earlier Big Crunch, however, the explosion of the Big Crunch could happen before all the matter has fully crunched, would this explain the odd scenario today of mismatched age of galaxies throughout the universe? Okay, let me think about that question. Okay, so we know that the universe we live in currently is expanding, and this expansion is accelerating. The universe is accelerating faster today than it was in the past. This means that the universe is getting bigger and is getting bigger faster than it has at any point in the past. Now, this means that the end of the universe right now, as it looks, could be two possible scenarios. The universe could either keep expanding forever as it is now, and everything will gradually get further and further away from everything else, and the universe would end up as a cold, dead, empty, desolate wasteland where there's no communication between anything, no exchange of energy, no exchange of information. Not a fun scenario. Option number 2, the accelerated expansion of the universe increases. We get more accelerated expansion, and it increases so much that the expansion of the universe is strong enough to pull atoms apart at the particle level, to rip protons away from neutrons, to rip apart the quarks inside the protons and neutrons, basically to disintegrate the entire universe. So if the accelerated expansion of the universe speeds up, gets even more accelerated, then the whole universe could rip itself apart, and we'd end up in what is known as the Big Rip. And in this case, the whole universe is disintegrated. Also not a fun scenario. All of these end of the universe scenarios are like hypothetical future scenarios. We don't need to worry about it just yet. Planet Earth will burn long before any of this happens. But before we knew that the universe was undergoing accelerated expansion, when we thought it was just expanding, there was another idea of how the universe could end, which would be a big crunch. Now, if you imagine the universe is a constant battle, we have gravity pulling things inwards, and we have the original expansion pushing things outwards. So if we ignore the fact that the universe is accelerating right now, what you'd expect to happen is after this initial expansion, which we call the Big Bang, but the Big Bang is a lot more than just this initial expansion. But if we have this initial expansion, hello, Otto. Yeah, you can come up. It's okay. As long as you're not in the trash room, you can come up here. Okay, Cat, as you can see, you saw a tail. He's now sat happily on my laptop, which is good. He's over there. He's not in the trash room anymore. So, before we knew that the universe was undergoing accelerated expansion, we know that the universe is expanding as a result of this initial expansion, but this is gradually going to slow down as it runs out of energy. This will cause gravity to take over, and then everything in the universe, all of the massive galaxies, all of the stars, everything that we have, would gradually attract everything else again, causing things to collapse back upon themselves. This is what it would be known as the Big Crunch, where instead of expanding, the universe starts contracting and collapses. All of the matter goes back to one singularity, which is just a point where our equations break down. That's what we mean by singularity. So in the Big Crunch scenario, after the universe is done expanding, everything collapses back upon itself. However, this would result in a huge amount of energy concentrated in a very small space, because everything in the universe has energy, everything has, or a lot of things have mass, particles don't, some particles don't, but there's a lot of energy in the universe. If you condense it into a very small point, you have a very, very small point with a lot of energy, which kind of sounds like exactly what you would need to trigger another Big Bang and therefore another universe. So this is, please don't disconnect my cables. It's just trying to disconnect the cable that is connecting my camera. I'm not sure if you all saw it flicker. I saw my screen flicker. Do not disconnect the cables. Now, my cats are full of mischief today. I guess mischief is indeed a Sunday evening thing. Okay, so if you imagine the cyclical idea of the universe, you would have alternating expansions, big crunch, expansion, big crunch, which would kind of lead to the universe doing something. I'm going to draw a picture here. Something like this, where, you start from somewhere, you have a universe, it contracts, and then it expands again, then it contracts again. So you have a big crunch, a big bang, a big crunch, a big bang, and so on. So this was the idea that you would have big crunch, big bangs. However, we have I'm getting back to your specific question, James, don't worry, I'm getting there, just providing context. So what I was going to say, however, all of the evidence we have currently points to the fact that the universe is not heading towards a big crunch, which also begs the question of, would it have had a big crunch before? Does it make sense to consider previous cycles of this expansion and reduction, if we know that today that is not the universe we live in? So let me answer first how we know that we're not heading towards a big crunch, and then we can talk about the specifics of your question of what would happen if there were a big crunch anyway. Okay, so there are several ways we know that the universe is currently expanding. And we know what is causing this expansion, we think. So if we look at what the universe is made of, we know that the universe has three main components today. Let me just bring up a picture. This is not the slide I want to show you, but you all know it takes me a minute to change slides. I will come back to this slide. Don't worry, this does not count. This does not count as my CMB because I didn't mean to show it. Okay, so the universe, as we know, it has three main components. Everything we see, everything we're used to, everything from my very mischievous cats to my cup of tea that I completely forgot I had. All of this is normal matter. Normal matter only accounts for about 5% of the energy budget of the observable universe. Perfect temperature. There is another 26% in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but doesn't interact via the electromagnetic spectrum, which means dark matter is essentially invisible. We cannot see dark matter, but we know it's there due to its gravitational interactions. And then we have 69% in the form of dark energy. Now, dark energy is a type of energy that permeates all of space-time. You could call it the modern-day ether if you wanted to, not a one-to-one relationship again. And dark energy is a kind of repulsive energy. So dark energy is what is pushing the universe outwards. Dark energy is counterbalancing the gravitational force of normal matter and dark matter, and it is pushing the universe outwards. It is pushing the universe outwards faster than it was in the past. As you can see, there is a lot of dark energy. Based on the way that dark energy behaves throughout the different phases of the universe, we know it wasn't that dominant in the past, but it's more dominant today, which is why the universe is accelerating. If we go to, I believe the next slide should be the one I want. Yes. If we go to the standard picture, actually, let's do the next one, which I think you'll like more, especially after someone made a connection as to what this looks like, which we do not discuss. If we look at this kind of history of the universe figure here, you can see there's this initial Big Bang. We don't know exactly what that was. There was this initial point. Then we had this rapid growth, which we call inflation. Then it's been pretty constant, but where we approach the today part, you can see it starts branching outwards. I actually think the previous slide shows this even better. You can see here today, it starts branching outwards again. It's been consistent for a while, and now it's branching outwards. The reason for this is it was expanding, but the acceleration of this expansion only started fairly recently on cosmic scales, like 1 billion or 2 billion years ago, based on when dark energy turned on in the universe. It's always been there, but based on the way that these different species, the dark matter, the normal matter, the dark energy, based on how these behave throughout the history of the universe, we know that today the dominant contribution is dark energy, even if it was also the dominant one in the past in terms of energy. In terms of effects, today it's the one that has the biggest effect. So, to answer the question that we had here from Plath of what could fuel the expansion of the universe till the point of the Big Rip, dark energy. Because we don't know exactly what dark energy is, and we don't know what dark energy is doing, then we don't know exactly what dark energy is going to do in the future. So, before I get into what dark energy is doing in the future, just want to briefly say, how do we know these numbers? Where does this 5%, this 26%, and this 69% come from? That is an excellent question. And the answer, of course, is the slide you all knew was coming, the cosmic microwave background radiation, this thing here. This is a snapshot of what the universe looked like 380,000 years after the end of inflation, or about 13.5 billion years ago from today's perspective. This is a snapshot of the first light in the universe, the first image we have of the universe. What you can see here is kind of the circle around us of the first light. Red spots indicate slightly more energetic, blue spots indicate slightly less energetic photons, particles of light. This map here comes from the fact that in the early universe, we had three main components. We had protons, we had neutrons, and we had electrons. Sorry, no, forget the neutrons. We had protons, we had electrons, we had photons, which are particles of light. In the early universe, all of these three were constantly interacting. The photons, the particles of light, could not travel freely. As we said before, when we're talking about photons traveling through a medium, in this case, they were traveling through the plasma. They were traveling through the kind of the proton-electron swarm, and therefore they were constantly getting absorbed and re-emitted, and therefore the photons, the particles of light, could not travel freely. As the universe cooled down, the protons and the electrons could combine together to form the first elements in the universe, and at that point the photons could break away. They were no longer being absorbed and re-emitted because the electrons were now bound up with the protons. So the photons, the particles of light, could break away. They have been traveling freely ever since. Their wavelength has shifted as they've been traveling through the universe. So today they're in the microwave range of the electromagnetic spectrum, and they are behind everything else in the universe, which means they are the cosmic microwave background radiation. Background because it's behind everything else. Cosmic because it's in the cosmos. Microwave because that's where it is in the electromagnetic spectrum. And by looking at this, by looking at how many orange photons, how many blue photons there are, by looking at the statistical properties of this map, we get these very, very, very exact figures here. We get the fact that there are 4.9% normal matter, 26.2% dark matter, 68.9% dark energy. However, there is something that this amazing picture doesn't tell us. Where did my amazing picture go? Oh, I tried to change with the keyboard. I forgot that my keyboard is turned off because of a certain cat who wants to stand on it. This amazing picture here, I can't believe I just did the finger guns. This amazing picture here, there was one or several things it doesn't tell us, but specifically in this case, one thing that the cosmic microwave background radiation cannot tell us, and that is exactly why that keyboard was turned off. Thank you, baby. Yeah, you can. Okay, they're both ready to sleep now. So, one thing that the cosmic microwave background radiation doesn't tell us is what dark energy is doing and what dark energy is going to do in the future. Like we have a pretty good idea of what it's doing now. Now, we don't know if dark energy is constant in time. There's something that defines how dark energy works, which is called the equation of state parameter, which is a fancy word for basically saying how it behaves. And this is something that we can't measure precisely from the cosmic microwave background radiation because that is I guess he's not done. That is one snapshot in time. In order to study dark energy throughout the history of the universe and make predictions of what it's going to do in the future, we need more snapshots. One way of doing that, for an example, is looking at galaxies. The further out into the universe we look, the further back in time we're looking, which means if we construct a map of galaxies around us, looking further and further out into the cosmos, we can get an idea of what galaxies are doing today and what they were doing further and further back in time as we look further and further away. Because galaxies are big gravitational objects, the way that they interact with each other, the way that they behave, is given by the combination of gravity and dark energy pulling things outwards, which means we can use these snapshots of different parts of the evolution of the universe to figure out how dark energy has been evolving. And if we do that, we still are not completely sure what dark energy is doing, but it seems like there are two possible ways dark energy could go. It can either keep doing what it's doing, which means we head to the heat death, or the big freeze, if you want to call it, where everything just gradually gets further and further away from each other, the universe keeps expanding. Or then we enter the big rip scenario, where dark energy increases and this rips apart the atoms. To answer Prath's second question here, would space continue expanding even after the events of a big rip? Yes. Even if you rip everything apart, the universe basically disintegrates. All of the matter in the universe disintegrates to its base components. The expansion will keep going and going. So not only would the universe tear itself apart, the individual particles would then be flung so far apart from each other that you would never be able to restart. You would never be able to have more matter, more structures, because all of the individual particles at that point are so far away from each other, they stop interacting. So, what could fuel the expansion of the universe till the point of the big rip? Dark energy. Would space-time continue expanding afterwards? Yes. Now, there's a question from Paul here, and I'm going to come back to the big crunch and what would happen, big crunch scenario. Still need to come back to the original question. I've gone on several tangents since the original question. Question here from Paul: how sure are we that the dark energy is constant? We are not sure, especially because the latest results from DISI, the dark energy spectroscopic instrument, seem to show that dark energy is thawing slightly. So it is slowing down in a sense, but not dramatically. Now, follow up from Paul: if it changes over time, might it reverse into a contraction? Given where we are now with dark energy, it doesn't seem likely that we're going to head back to a big crunch scenario. Dark energy would basically have to completely stop what it's doing, completely shut off, in order for it to slow down, for it to then stop the accelerated expansion and allow gravity to take over and force things to collapse again. So even though we don't know exactly what dark energy is doing, or what dark energy is going to do in the future, unless dark energy basically just turned off completely or disappeared completely, we are not heading towards a big crunch. Now, of course, we don't know exactly what dark energy is. We don't know exactly what it's doing. But it doesn't seem overly plausible for dark energy to just completely stop. You'd need something very dramatic for that to happen. And none of our models or theories really show that option at this point based on the data that we have. Based on the fact that we can see that the universe is undergoing accelerated expansion. We know this from things like the way supernovas look. Supernovas are dying stars that explode and produce a specific amount of light. And we can use the light we get from supernovas to very accurately measure distances and velocities of nearby galaxies. And this is how we know that the universe is undergoing accelerated expansion. I love when I get to tie in my prompt questions. As you will know, there's some random questions in the YouTube description, which are just whatever I come up with on Sunday morning when I set up the stream. And I always try to then bring them back in and tie them in. And I know there's a question that I put today. One of the prompts is, why are supernovae important? So supernovae are stars that have reached the end of their lifetime. They explode very dramatically. This explosion produces a specific amount of light. And by looking at the light we get from this, which is something we can calibrate very well, we can basically use them as a way of measuring distances, which allows us to see that all of the galaxies that we can see, except Andromeda, our close by neighbor, all other galaxies in the universe are moving away from us, and they are moving away from us faster than the speed of light. Sorry, not faster than the speed of light. Absolutely not. They are moving. I just read another question and got distracted there. They are moving away from us faster than they were in the past. So by looking at supernova exploding stars in other galaxies, we can figure out the distance to these galaxies. We can figure out how fast these galaxies are moving. What we've seen is that all close by galaxies, except our very closest neighbor, are moving away from us, and they are moving away from us faster than they were in the past. This is what gives us the idea that the universe is undergoing accelerated expansion. So, as I was saying, based on everything we know about dark energy right now, it is unlikely that we head to a big crunch scenario. Now, back to the original question. Let's assume, like, okay, what if we did? Or what if in the past there were a big crunch scenario before our current universe? What if we come from a universe where there was no dark energy, there was a big crunch, and our universe now has dark energy, and there won't be a big crunch? What if we're the ones that break the cycle? This is hypothetical. This is not what we think is happening. But a comment from David, that's what the big red button does. It switches off dark energy. Yeah, maybe I shouldn't press the big red button if it turns off dark energy. Although the universe collapsing upon itself, not a bad way to go. But let me just go and reread the question that I'm supposed to be answering, because I am answering something completely different. I'm answering tangentially relevant things. And okay, my tea is almost gone, but it's now just in the window, like 45 minutes after I made it. It's approaching the point where it's almost too cold. In fact, let me just finish my tea. I was going to say it's not even a tea, it's an infusion, but it does have rooibos in, so it is technically a tea. Okay, now back to James's original question. If the Big Bang is a result of an earlier big crunch, now we have context. However, the explosion of the big crunch could happen before all the matter has fully crunched. Would this explain the odd scenario today of mismatched age of galaxies throughout the universe? Okay, so when we look at galaxies today, there are some galaxies, a few, not many, there are some galaxies that have different ages to what we would expect. They all fit within our current picture of galaxy evolution for the most part, but it's not always a one-to-one relationship. You'd expect the further out in time you look, because the further out into the cosmos you look, you're looking further back into the past, and therefore you should see older galaxies. You're like galaxies that are technically younger in their evolution, galaxies that were formed longer ago from our point of view. So you look at the kind of baby galaxies because you're looking back into how they looked billions of years ago. However, sometimes you find some anomalies where galaxies that are a bit further out look a bit older than they should be, and vice versa. But these are kind of accounted for within our current understanding of galaxy evolution. Thank you for stopping by, Taz. It was great to see you here as always, and good night. Wonder what time zone you're in. I guess further to the east. Okay, so I just I have no idea what people's bedtimes are. So the question that James asked that I'm answering in a roundabout way is, when let's imagine a big crunch is happening. What if before everything has crunched back upon itself, you start a big bang, you start the new universe? What happens to all the matter in between? Now, let's assume that in this new universe still behaves approximately the way our universe does. So let's say our universe came from a big crunch. Now, first of all, we need to think about the big crunch. If gravity is pulling everything together, it's also going to pull galaxies together. Now, we're pretty sure that at the center of every galaxy, there is a supermassive black hole. The supermassive black hole has a lot of stuff orbiting around it. It has a whole galaxy around it. If we're saying that dark energy no longer plays any role, and the whole universe can start collapsing upon itself, everything starts getting closer and closer, the galaxies are also going to start getting more and more compact. So the galaxies are going to start shrinking, not completely, not everything is going to fall into the black hole immediately, but it is gradually going to get more and more noticeable, especially as more and more galaxies come together. It's going to kind of accelerate this, where you're going to have a lot of mass infalling into a lot of other mass. But let's say that doesn't happen. Let's say you have an intact galaxy and the big crunch happens. Now, after the big crunch, we enter our new universe. Let's say it looks like our universe. Now, we're pretty sure that in the early universe, there was a phase known as inflation. So inflation is this kind of exponential expansion that the universe went through. If I bring up my slides again, let me just bring up my slides and change slides. Also, I'm surprised nobody commented that it took almost half an hour to get the CMB today. That's a ridiculously long time. The CMB should appear much, much earlier than half an hour into my streams. But there is the CMB beach ball in the background, and the CMB is in the Cup of Cosmology logo, although I know you all don't count that one. Okay, actually, I want the second one this time. I do want the condom version. This perfectly innocent one. So this is our map, our kind of picturesque version of how the universe has behaved since the Big Bang until today. Again, the Big Bang is not a specific moment in time, it just refers to the beginning of the universe. So let's say this came from a previous big crunch, everything has collapsed. Now we enter the universe as we know it. So we have a lot of evidence that the universe went through this phase of cosmic inflation. Now you can see here that we go from a small point that starts expanding to suddenly this whoosh outwards. This is inflation. So during inflation, we believe that the universe grew exponentially. So it got dramatically big in a short amount of time. We have a lot of reasons to believe this, including the way the cosmic microwave background radiation looks. Now, if you have a period of cosmic inflation, everything in the universe gets pushed away from everything else in the universe dramatically. Anything that had been in what we call causal contact, so able to exchange information, will get pushed to the point where it is no longer in causal contact with each other. So this means that even if we're coming, let's say hypothetically, we're coming from a big crunch where there was an intact galaxy, and then the new Big Bang happens. In this new Big Bang, or this new universe, the first thing you're going to encounter is inflation. Inflation is going to push everything away from everything else extremely quickly, to the point that even if we had this intact galaxy, it would not survive inflation. But let's say it did. Just for argument's sake, let's say this galaxy survived inflation, which by now is a lot of hypotheticals, but let's say it survived inflation. This galaxy would be pushed so far away from anything else in the universe that it would no longer be in what we call causal contact, which means it would no longer be able to talk to us in any way. Now, this is very much supported by what we call the homogeneity and isotropy of the universe. So the universe looks the same in every direction, regardless of where you look, approximately. Obviously, looking at the sun is very different to looking at the moon. But on large scales, if you take a step back, no matter where you look in the universe, it looks pretty similar. And this is especially noticeable in the CMB. I'm going to bring up my beach ball now because it's easier than bringing up the slides again. You can see that, there are some differences. There are some hot regions here and some colder regions up here. We have this really hot band in the center of the galaxy. We can ignore it. We have like bluer regions here. We have slightly redder regions down here. But it is approximately the same, Wherever you're looking, statistically, this looks the same. So there is the question of if let's say the blues and the reds here show us the energy or the temperature of these photons, of these particles of light. These temperature differences are around 1/100,000th of a percent, 1/100,000th. So 0.001%. That is how different these photons are in terms of temperature. So this is a really, really, really small difference. So we have to ask the question of how come every photon, every particle of light that we see from different parts of the universe, you can look in any direction in the night sky, behind everything else, you have this cosmic microwave background radiation. And regardless of whether I take my measurements over there or over there, of this patch of the sky or this patch of the sky, remember, we're at the center of this ball, this is around us, this is the background we see behind everything else. Regardless of where we take these measurements, these photons are almost the same temperature. So the question we have to ask is, why are these photons almost the same temperature? What causes patches of the universe that are so far apart to have the same temperature? And our answer is that these parts of the universe used to be touching, they used to be in causal contact. So this means that they used to be able to exchange information, and therefore they reached the same temperature, they balanced out. So this is one of the reasons we know that the universe went through inflation, because otherwise it's very hard to explain why these photons have the same temperature. There's also other things like the fact that the universe looks flat, even though there's no reason for it, but inflation gives you a mechanism for that. I think we talked about the flatness of the universe in the last stream, so I'm not going to go into too much detail about it. Ask follow-ups if you want. So yes, we have this idea that our universe went through a phase of inflation. In my sketch here, this is what I've shown, this would be the big crunch, and then we have this immediate burst here, which would be inflation. So if inflation happens, let's say we're in this hypothetical case where hypothetically there was a big crunch and the galaxy made it from the previous big crunch to today, and this galaxy somehow somewhat survives inflation, by now, this galaxy would not be within where we are today. And if it were, we would see traces of it in things like the cosmic microwave background radiation, because it would mean there's a patch of the universe that would be warmer, where you'd have more stars. Now, we do know that there are regions of the universe where you have more stars, more galaxies, and regions where you have fewer. But this can be explained with the same thing that caused these temperature differences, which are quantum fluctuations stretched during inflation, basically tiny vibrations that got big. If there were galaxies that survived from a previous big crunch and into our universe, they would either be completely torn apart by inflation, or they would be pushed so far apart that we would not see them today. They would be so far out in different patches of the universe. They would be behind the CMB, and we would not be able to see them today in any meaningful way. So, to answer your question, James, which we took a long route to get here, but we got here. If the Big Bang is a result of an earlier big crunch, which we don't think it is, and the explosion of that previous big crunch happened before all of the matter had fully crunched, which we don't think it could happen, but let's say it does, would this explain the odd scenario today of mismatched age of galaxies throughout the universe? No, it would not. I love the question because it let me go on many tangents to explain many things. Short answer is no, it would not, because these galaxies would not survive either the Big Crunch or inflation. And even if they did survive all of these things, we would not expect to see multiple of these within our observable universe today. Observable universe being every part of the universe that has had time to send us information. Now, we know that the age of the universe is limited. The universe has been around, our universe has been around for 14 billion years. We know that light travels no faster than light in a vacuum, which means there is a limited patch of the universe that we have access to. And this is what is known as the observable universe. The boundary of the observable universe is the CMB, the cosmic microwave background radiation. And I think beyond that is outside of our observable universe. So, given inflation, everything inside our observable universe was basically a tiny part in the Big Bang. Any galaxies would be pushed beyond our observable universe during inflation. Now, of course, the next question is, we know that the universe is currently undergoing accelerated expansion. This means that things that were pushed outside of our observable universe could at some point re-enter our observable universe. The way to think about this is during inflation, everything pushes away. Now, as the universe is expanding, things that were pushed away come back into view. Objects in the rearview mirror are getting closer than they seem to be. I don't think that's how the song goes or the phrase goes, but you know what I mean. These objects, these things that were pushed outside of our observable universe at some point could re-enter. So, next question, as we're down this hypothetical path, let's keep going down this hypothetical path. Let's imagine there was a big crunch, a galaxy survived, it survived inflation, it got pushed outside of our observable universe. Dark energy keeps doing its thing. The universe keeps undergoing accelerated expansion. Could this galaxy ever re-enter our observable universe? Hypothetically, yes. However, at this point, we're talking about a galaxy that has undergone, it's survived one big crunch, it's made it through. All of the original stars would have long since died out. We know that stars live on average 9 billion years. Our universe is about 5 to 10 billion years, depending on the star. We know that our universe is about 14 billion years old, just shy of 14 billion years old. So even if this galaxy had undergone all of that and survived, it's unlikely it would still have survived 13 billion years to still be a galaxy today. So my answer is no, we could not have any galaxies, or if there were any galaxies from a previous big crunch, it wouldn't explain the slight anomalies in the ages of galaxies that we see today. However, this is also a scenario that I don't think would happen for several different reasons, but it is a super cool thought experiment. So this was an excellent question, James. Thank you. We got to talk about end of the universe scenarios. We got to talk about big crunch, which is always fun, and dark energy. I got to throw the CMB at you. Just you all know I'm always waiting for an excuse for the CMB to appear. We get to talk about homogeneity and isotropy and observe the kind of cosmic observable universe limits. Very cool question, very cool topics. The center of the observable universe is your eyes. You are not wrong, Paul. You're absolutely not wrong. When we are talking about the observable universe, we are talking about the patch of the universe that has had time to send information to us, the observers here on Earth. This does not mean we are the center of the universe, but it does mean we are the center of the observable universe, and every observer has their own observable universe. Now, of course, here on Earth, when we're talking about looking into cosmic scales, the difference between me being up here and someone being, a few hundred kilometers that way or a few hundred kilometers that way, a bit more than a few, no, this is not going to make much difference in terms of our observable universe. But it is true that the observable universe is centered around an observer, which means the observable universe is centered around us. Any possible civilization out there would have their own observable universe, which also means that other possible civilizations out there might see a slightly different version of the cosmic microwave background radiation on my beach ball. Which leads to the very fun question of how far away would you need to be in order to see a completely different realization of the cosmic microwave background radiation. Now, of course, we'd expect it to have the same statistical properties, but it would look a bit different. So how far away would you need to go in order to see a completely different observable universe? Or phrase a different way, how long would we need to wait to see a completely different cosmic microwave background radiation, a completely different observable universe? This is actually a question we set our graduate students in the course of perturbation theory in cosmology, which is basically how you get cool stuff like the cosmic microwave background radiation and galaxies out of this initial inflation cosmic soup thing. And we call it perturbations, which basically means tiny, tiny vibrations. So in that course, which I was the teaching assistant of when I worked in Germany, one question we set on the exam, the final exam for the students, was how far away would you need to be to see a completely different version, or like of CMB that is like 10%. We gave a specific percentage, cosmic microwave background radiation that is this percentage different from the one we can see. And you had to go through all the calculations of kind of like distances and stuff. And it might actually have been in general relativity that we set that. Was it in general relativity that we set that? Yeah, I think it was actually general relativity where we set that question. Yes, because then you deal with the expansion of the universe. Thank you for stopping by, David. Great to see you as always. Okay, so just completely lost my trail of thoughts there. Where was I? Yes, exam question for the students. How far away would you need to be to change the observable universe? It's a very cool question. The answer, if you're doing it like how far back in time or how far in the future, the answer is about 10,000 years. This is how long you'd have to wait to get a completely different CMB. If you want to do it in terms of distance, 10,000 light years away. Because light years are in fact a unit of distance, not a unit of time. Sorry, no, other way around. Light years are in fact a unit of, yes, how much light would travel in a year. It's a distance. Okay, YouTube is restricting the length of comments? Really? I did not know that. That is unfortunate. Well, feel free to break it up in multiple and just put like part 1, part 2, part 3, and I will gradually piece it together. There's not too many comments today anyway, so I can gradually piece it together. And as always, if you have longer questions that don't fit here, feel free to email me. I will say that, as some of you know, I am very bad at replying to Cup of Cosmology emails. Also, because I literally only have the Cup of Cosmology emails active on one device, and it's a device that I don't use frequently. I basically use it on Sundays for my live streams. So sometimes I can take a week to reply to emails, if not longer. Apologies for that. I know I miss an important email for like 12 days, but I do reply to them eventually. So yes, if you have longer questions that don't fit in the YouTube chat, feel free to send me an email. I will read them and then I can answer them in a future stream. So wrapping up what we were saying, some excellent questions here from James about big crunches and galaxies, and will galaxies survive to today? And the short answer is no. But as I was saying, if you wanna flirt with someone, you can tell them that, you and I are the center of the observable universe. You are the center of my observable universe, which is technically correct. They are not the center of the universe, but they can be the center of the observable universe. You can caveat your flirting with physics. That's got to work, right? Yes. Okay, so Yes, we are the center of our observable universe, and the background of our observable universe is the cosmic microwave background radiation, which is very cool. And I have it on a beach ball. Also, I have it on a mug and a t-shirt and in like 3 places in front of my desk in the office. Because as you all know, I love the cosmic microwave background radiation. Also, I have a beach ball, which is a perfectly legally acquired beach ball. Someday I'll tell you the story of where this beach ball came from, but not anytime soon. Okay. There are 2 more questions that I see here. We're going to do a couple more questions. We still got a while to go. You know, these streams used to be 60 minutes, and at some point you will convince me that the stream should be 90 minutes. So now we go for like an hour and a half. Okay. Question from Chocolate Cyan. Love the username. Do you have a favorite pet peeve about cosmology you've seen depicted in movies? Ooh, where to start? So I have a few. Actually, there is a whole stream we did, which is on YouTube. It's not linked under my account, but it should be on YouTube. I can link it. I can link it somewhere. So back in the days when Copper Cosmology was on HAPS, there were a group of scientists who were doing regular live streams, and we had a neuroscientist in the mix. We had another physicist in the mix. We had some biologists. We had an entomologist. Super cool, super fun mix. And we actually did a whole live stream about pet peeves in media, and we all talked about it from our different scientific perspectives, and it was basically 90 minutes of us ranting about things like this. It was so fun. Yeah, if you search for HAPS Science Takeover, you'll probably find us. I can link to it. I will try to remember to put a link to it in the chat or in the description so that you all can go check it out, because I don't think it's linked to my channel in any way. Okay. Yeah, beach ball lure drop once the statute of limitations lapses. Very much so. Once I can tell you where the ball came from, I absolutely will. There's like a handful of people who know where it came from. Not that they were in any way involved in the beach ball saga, but point is, I have a beach ball. It doesn't matter where it came from. I'll tell you someday. There will be a lure drop someday. So, what are my favorite pet peeves about cosmology? I love science fiction. And I am very willing to do the suspension of disbelief thing and, believe whatever universe they want to create, provided they don't try to use scientific sounding words that do not make sense. One classic example, no hate for Doctor Who, you'll know I love Doctor Who. Reversing the polarity of the neutrons makes no sense. They don't have polarity. How can you reverse it? It doesn't make sense. So I'm all for force fields and warp drives and things like that, because those are things that are hypotheticals. They're fun to think about. They're fun to play about with. What I don't like is when people use scientific words completely wrong. And examples of this are there was like one that really annoyed me recently, where I think it's Another Life, Afterlife. It's a super weird sci-fi show. Absolutely do not recommend it. But at some point they're traveling through an asteroid field. Also, asteroid fields not scientifically accurate. If you're traveling through an asteroid field, it's a breeze. The next asteroid is like hundreds of kilometers away. Asteroid fields are not super dense. Asteroid fields are largely empty, as is most of the universe. But in this specific show, they're traveling through an asteroid field. And then things get weird and they start seeing like light beams shoot past them. And one of the scientists says, "Oh, this light beam, it's accelerated dark matter." Dark matter, as in the thing that is main property is that it is invisible. It is not light. It does not glow. And they're like, "Oh yes, dark matter accelerated and now it's visible, and that's what we see shooting past our ship." Call it anything else. Call it a tachyon if you want. Hypothetical. Call it flubber. I don't care. Don't call it dark matter. Those words have meanings. That is one of my pet peeves about cosmology in media, is when people do things like that and use like actual scientific concepts really incorrectly. And the reason that annoys me is because it makes my job of being a science educator harder, because then I get people thinking that dark matter, if you accelerate it, is a light beam. And that's incorrect. So I'm all for playing about coming up with new science stuff, coming up with random stuff that sounds plausible. Force fields, hypothetically, they could work. lightsabers. I'll buy it. But don't call it dark matter when it's not dark matter. Like, don't use an actual scientific concept and bend the rules. Rules exist for a reason. Rules should be broken in specific cases, not in this case. Yes, I love this question because it is something I will absolutely enjoy answering. I have a lot of pet peeves. I have many things I like ranting about. In general, I'm very happy to suspend my disbelief. Do time travel movies get it right? Absolutely not. 99% of time travel media does not understand the implications of time travel, and if they did, their whole movie or TV show would not make sense. I'm willing to go with that. I don't mind. But when you use actual scientific concepts, another one, Interstellar. You're going to get me going on a tangent here. I will come back to the other questions later, but now we're going on this tangent. Interstellar, great depiction of time dilation, great depiction of black holes, very, very scientifically accurate. Loved it. Right up until spoiler alert, if you haven't seen Interstellar, meet me for the next 1 minute. It's been out for a while. You should have seen it by now, but this is your spoiler alert warning for the end of Interstellar. Black hole scientifically accurate, time dilation scientifically accurate. And then they jump into a black hole, travel back in time into the kids' library. What the actual? No, they spend, I don't know, 5 hours. How long is that movie even? Let's talk about time dilation. They spend so long being scientifically accurate, and in the last 10 minutes, the power of love and library magic saves them. No, not how it works. Yes. Another pet peeve, the ending of Interstellar. Okay. But there's a bunch of other ones, there is no sound in space. Space battles would be pretty less dramatic, but of course you need the pew 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 pew. Star Wars, you need the lasers. Fine, I'll accept that. Yes, I do really enjoy sci-fi. I will complain about it a lot. I do really enjoy it. Another pet peeve, and this is going to be the last one because this is a long tangent. Just reading some of the other pet peeves here. One from Paul: pet peeve in sci-fi space battle scenes, sci-fi battle scenes, ramming speed. There's no such thing. You just accelerate and try to ram. Yes, what is ramming speed? It doesn't make sense. Comment from Prathia: my pet peeve has become correcting every unscientific use of theory to hypothesis. Yes. Now this is a general thing where when scientists use the word theory and hypothesis, it carries weight. It has a specific meaning. However, it is not the same meaning that is used amongst non-scientists. So, if I wake up one day and see that the floor is wet, I might say, I have a theory that it rained overnight. That is not a scientific theory. That is a hypothesis. And the reason this is a problem is that people then equate the two. So then when I talk about the theory of gravity, for a lot of people, this is on the same footing as, I think it rained overnight because the ground is wet. It could be that someone just cleaned the ground. So this conflating that the media does of theory and hypothesis does actually degrade the credibility of scientific theories to the general population, because when I say something is a theory, I mean it's a scientific theory, which means it passes a lot of tests, it has all of this rigor behind it. But in movies, and in general, when people are talking, that's not how we use it. This is not just media in general. This is just a lack of clarity about what our words mean. Also, probability. If I say something is 99.9% sure, from a scientific perspective, what I'm saying is this is probably true, but I'm never going to say 100%. But what other people might hear is it's not 100%. Why is it not 100%? So I think the theory and hypothesis thing goes deeper than just how it's portrayed in movies, but more towards the fact that we mean different things sometimes when words have different meaning in different contexts, and people don't always appreciate the nuance. Back in the early days so before Cup of Cosmology was a live stream, Cup of Cosmology was a blog. There is an old blog that still exists on Blogspot. So it's cupofcosmology.blogspot. I believe de, because it was in Germany, might even be .com. Anyway, there is that old blog. And there were about 10 blog posts there. And one of them is a whole rant about what the word theory means. Now, then Cup of Cosmology became the name of the show. There is a new blog on cupofcosmology.com. Please do not expect any blog posts. There are 2 there. It has not been updated in a long time. And I wanted to migrate all of those old blog posts to the new blog. But I didn't, because I decided that ranting about the difference between theory and hypothesis is not valuable. I get it is something that I care about deeply, but also it gets into the kind of territory where we just become pedantic scientists correcting people. And I don't want to do that. If you want to call something a theory or a hypothesis in a non-scientific context, go ahead. I will not begrudge you that. However, when talking about scientific concepts, it's very important to keep these 2 distinct. Okay, final pet peeve I'm going to talk about. I have so many pet peeves I can talk about, even outside of this topic. Just pet peeves in general. I have so many pet peeves in general. Like the word guesstimate. Do not get me started on the word guesstimate. Okay, but talking about like pet peeves about cosmology, I'm going to say the way that cosmologists or astrophysicists are depicted in media. Because you get 2 brands of cosmologists or scientists in general in media, you get 2 brands. You get the crazy old scientist, white hair, lab coat, or you get the supermodel. And there is no in between. You pick any scientist, especially cosmologists, from any movie or any TV series, and you either get the crazy genius or you get the supermodel. And then they do things like, let me just run my cosmology experiments on a laptop. Wait 10 weeks? It takes time. Cosmology is not eureka moments. Cosmology is a slow and gradual progress, but not in sci-fi. In sci-fi, they're like, I'm an astrophysicist. I can calculate the trajectory of this asteroid in 3 seconds. No, you can't. Yes, it will take a while to run the simulation. Yes. Pet peeves, there are many. However, that said, I do love a good sci-fi story. I do love a good fantasy, and I'm willing to ignore all of the rule breaking. I'm willing to ignore when Han Solo completes the race in 12 parsecs. It's not a unit of time, it's a unit of distance. Anyway, may I introduce you to a proxy guesstimate? You may not. Absolutely not. Guesstimate. My issue with guess. Okay. Tangent. Tangent on a tangent on a tangent here. Tangent. Language evolves, language is fluid. The whole point of language is to communicate, and it should evolve, it should change. We should be inventing new words. Shakespeare invented new words. We invent new words all the time. There are words that we use today that meant nothing 10, 15, 100 years ago. I'm all for a language being fluid. The purpose of language is to communicate, invent words, break the rules. Grammar is meaningless. However, my exceptions to all of this are combining words that don't make sense. A guess means you have no prior knowledge. An estimate means you're doing something like you have prior knowledge. And if you want something in between guess and estimate, you have an educated guess. Why does the word guesstimate exist? What does guesstimate add that is missed by either guess, estimate, or educated guess? Nothing. It's a pointless word. And it's a factually incoherent word. You cannot add guess and estimate together. Okay. Rant over. Rant over. Talking of pet peeves, that one just had to come up. As to a proxy guesstimates, no. I refuse. Okay. I am a very calm and composed person. Thank you, Chocolate Cyan, for was that even the username? Yes. Thank you for the question about pet peeves. I have many, but I will enjoy a good sci-fi show. I often don't care if it breaks the rules. I like when there are tiny details that explain why they're breaking the rules. You know, one of my favorite sci-fi shows, which is Farscape, has just like a tiny explanation at the beginning for why every single species speaks English, sorry. Like even the non-humans, everyone they encounter throughout the universe speaks English, because then they don't need to bother about languages, and there's just like one throwaway detail about this, and then you're like, okay, makes sense. Never have to question it again. Unlike Stargate, where it's just like, oh, everyone we meet on every other planet just happens to speak English, and we will never question it. At least, you know, if you're going to do stuff like that, give a reason. Okay. Very, very fun question. I could do a whole stream about pet peeves in media and name and shame, but you get the idea. I love sci-fi, but yes. A guesstimate is when your prior knowledge is in Schrodinger's superposition. but then it's a probability. It's not a guesstimate. It's words have meaning. Okay. Yes. There was another question I saw about the CMB and about dark energy. Moving on from pet peeves in sci-fi. love those questions. Okay. There was a question from Prath when we were talking about dark energy, when we were talking about the end of the universe and dark energy being what's causing the accelerated expansion of the universe, Big Crunch, all of that. Okay, there was the question from Prath. What if dark energy is a pseudo force, just like centrifugal force, because the universe is the singularity of a rotating black hole? Love this question. Yes, centrifugal force is not a real force, but it is a pseudo force in the sense that we feel its behavior. But yes, it is related to the conservation of angular momentum. Okay, so what if dark energy is a pseudo force? And the universe is a singularity, the universe is a rotating black hole. Okay, let's assume that the whole universe is a rotating black hole. This is a very cool question, Beth. I'm just thinking about how to go about answering this. Now, could dark energy be a pseudo force? I'm going to say no, because the centrifugal force, it does push things outwards, but it pushes things outwards away from it. If we're inside the rotating black hole, we would not be pushed out, we would be drawn inwards, right? Because of the balance of forces. So very interesting question. I'm going to have to think about that. But let's say, even if that is true, let's say that the universe is a rotating black hole and dark energy is a pseudo force, it's still not going to change much in terms of how it behaves, because we're pretty sure we know what dark energy is doing now. We think we don't know what dark energy is going to do in the future. But even if you have, let's say we have a rotating black hole and we live in the center, and dark energy is the result of this angular motion, which we don't think is the case, but let's just say hypothetically it is, it's still unlikely that this is going to stop spinning, right? Objects in motion don't just randomly stop. We have conservation of energy, we have conservation of momentum, there's not a lot of friction going on. So rotating black holes don't just randomly stop, which means even if we say that the universe is a rotating black hole and that's what's causing dark energy, which I'm not saying that's what it is, hypothetically speaking, then even in this case, dark energy is unlikely to just randomly disappear or stop or change its behavior dramatically. Which means, while we don't know what dark energy is going to do in the future, even if that's the cause of it, it's unlikely to suddenly disappear or go away because of the way it's acting now, and because that's not how you can't just stop a rotating black hole. You can't just make it stop and make the pseudo force that we're calling dark energy disappear. So it's a great thought experiment. I'm going to think some more about the exact implications that would have. But in terms of the discussion of like the end of the universe and what might happen there, I don't think having a pseudo force would change anything because of the things that we do know about what dark energy is doing currently. Great question. I'm going to think some more about that. I'm going to write it down. I'm going to write down pseudo force. See, the problem is I write things down quickly because I'm in the chat. So then my comments are just like photons slow down, pseudo force dark energy. And I'm going to add rotation here. And then I look back at my notes sometimes. I'm like, what? What does that mean? Yes. Also, fun fact, I know there's another CMB question I still need to answer. I will get to that in a sec. Specifically, the singularity of a rotating black hole. Yes, I mean, if you're in the singularity, you're beyond the event horizon. So in this scenario, and I'm imagining that the observable universe is kind of our event horizon of the rotating black hole, and we are in the singularity or in the center of the rotating black hole. But yes, cool question. Love the cool question. There's a comment here from James after I was ranting about the word guesstimates of let's talk about academia next. Yes. Let's not talk about academia. I love being a scientist. Academia, on the other hand, comes and goes. But currently, I'm actually in a positive mood about academia for now. Let's see how long that lasts, but at least for now, am I in a positive mood about academia? I'm not going to rant about academia because it's late in the day mood. Okay, before I answer the CMB question, oh, my voice is going. I've talked too much the last few days. Before I answer the CMB question, fun fact, I've ran out of notebook. This notebook, I have a stash of like 50 notebooks. I never run out of notebooks. You can never have too many notebooks. But that means that what I'm going to do before the next streams in a couple of weeks is go through and see if there are any open questions that I haven't answered. But the thing is, just looking here, there's random comments like quark degeneracy, question mark. What was the question? Who knows? Next page, stars, question mark. Energy conservation, question mark. So yes, now this notebook is literally falling apart. Quark confinement plus stars. So yes, I will look through this and try to make sense of my thousands of pages of writing. Apparently I do write like I'm running out of time sometimes. Hamilton reference. Where did you even come from? Anyway, point being, I will look through my notebook, so that means you might get answers to some of the questions soon, or more likely, I'm just going to stare at this and be utterly baffled by what Pathme was writing down here. As to the comment from Path of take this notebook to the office, we could have fun deciphering what I mean by stars, question mark, but unfortunately I don't write down the questions precisely enough for it to actually be useful, which I guess defeats the whole point of what I'm doing. Sometimes I write down questions to answer them later in the stream, and sometimes I write down questions to answer them at another stream, and then they don't get answered. Okay, just random tangent aside. Also, I'm not lacking in notebooks. I literally have about 20 notebooks right here, but you need the perfect notebook for each occasion, and I'm not sure which notebook is my next. This is not a notebook, it's a notepad. So I need a notepad for a cupboard cosmology, which means I need to go to that cupboard instead of that cupboard. Anyway, there was a CMB question I wanted to answer. Was there a CMB question, or did I just assume it was a CMB question? No. Yes. Comment from Ben. If someone on the edge of our observable universe sent us their CMB, that would be really cool. Unfortunately, it would take a while to get here because anyone on the edge of our observable universe is by now about 93 billion light years away from us, which means it would take 93 billion years for that information to reach us. Where do we get 93 billion? So glad you asked. Now, of course, observable universe. We can give a diameter, we can give a radius to the observable universe. So if they're on the edge of the observable universe, they're like 42 billion light years away, not 93, 42, 43, around that number. So the observable universe is, of course, this ball. We are inside, we are in the center. Now, we know that the universe is about 13.8 billion years old, which means when we look at this, we're looking at what the universe looked like 13 billion years ago. However, since like this patch of the sky sent us information, the universe has been expanding, and this expansion is accelerating. So when we look at this part of the sky that sent us these CMB photons, even though the photons took 13.5 billion years to reach us, by now we're looking at something that is 43 billion light years away because of the expansion of the universe. So this really means that when we're looking at these faraway galaxies or these faraway points on the CMB, we're not just looking we're seeing something that was produced 13.5 billion years ago, but today that point is much further away. It's like if I send something from here and then I go somewhere else, even though you got the letter from here, the person who sent it is now further away, if that makes sense. So when we look at the CMB, like this spot here, yeah, it was produced 13.8 billion years ago, 13.5 billion years ago. But by the time it's reached us, that point is 46, 42, 46, I always forget the exact number, 46, because then you double it, it's 92, yeah, 46 billion light years away. So the diameter of the observable universe is technically 92 billion light years, the radius is 46, which means to your question of where was my CMB question? I lost the CMB question again. Yes, where was my CMB question? I got distracted. I lost it. It was there, then it went away. Where did it go? Here it was. Yes, question from Ben. If someone on the edge of our observable universe sent us their CMB, it would be very cool. It would look very different to this, but it would take about it would take 46 billion light years to reach us if they sent it at the speed of light. And by then, our CMB would look completely different. So if we could have access to what the CMB looked like from the side of our, can you tell it's upside down? I can tell it's upside down. I think my brain has had enough. Not that it was that cogent when we started anyway. So if someone at the edge of RCMB sent us the observable universe or sent us their own beach ball, it would be super cool. Unfortunately, it might take a while for that to reach us, which is why we need sci-fi things like warp drives in order to get someone else's CMB. Okay, very cool question. Let me just check that I've answered all of the questions here. Then we can wrap up because we are fastly approaching the 90-minute mark. So much for the paperless office. Yeah, I get it, but also I love paper. Like some things I will use a blackboard, I will use my tablet, but you just can't beat the feeling of writing a bunch of equations on pen and paper and scrunching it up in a ball and throwing it to the cats once it's done. I'm all for a paperless office in general, but also, yeah, I'm just a huge fan of pen and paper. It's so much nice. I do have a tablet which is supposed to be one of the better tablets for writing. It's just not the same. Yes, I've heard of Remarkable. It's not the same. Just I'm old-fashioned. Give me pen and paper, unless you're doing calculations, and then give me a computer to do it for me. Okay. Quick comments here. Comment from Preth. Lots of comments from Preth. I think quark degeneracy was about if it exists the same way that electron and neutron degeneracy exists. I think that is correct. I seem to remember promising that I'd get an expert on to talk about exactly that. And gluon degeneracy is also on my list. Yes, gluon degeneracy. And quark confinement may have been about Hawking radiation in white holes. Might have been, could have been. I see you have better memory than me, Brass, for your own questions, which is probably good. Yes, anyway, I will go through the notebook. I will try to reconstruct some of the questions, and then I will ignore all of the questions. But I will try to answer some of them. I have promised some of these questions. And just as a reminder, at some point I'm hoping to get a guest to talk about neutron stars and quark confinement. At some point I'm hoping to get a guest on to talk about the latest results from the dark energy spectroscopic instrument from DESI, latest results from this as well, dark energy survey. And there's a couple of people in my office who have agreed to be on the live stream at some point. Maybe we can get where do stars come from? How are stars formed? Maybe we can get that as well. Yes, there will be some guests appearing soon. But before all of that, I need to announce next week's stream, because next week we're not doing a general Ask Me. And I think next week there is a topic. And there is a topic because there has been a topic request. So as a reminder, if there's a topic that you want me to talk about for 90 minutes, for an hour, for whatever, and it's longer than just one question, there is a way you can request a topic. You can go to cupofcosmology.com, go to the tab Get Involved, and there you can see all of the explanation about how you can request a topic. Basically, contact me if I agree to the topic, do a donation to an organization I support. Once you've done the donation, we set up the stream, and then I schedule it, and we do the stream. Do not do the donation without, do the donation if you want, but if you're expecting me to do the live stream, please contact me first, because I won't agree to every topic. But there has been a topic request, and we're doing it next week. And I love the topic request. It's going to be super fun. So next week, we're going to be talking about primordial black holes, and specifically how new observations of gravitational waves and from the JWST might be promising, not promising, for primordial black holes. Basically, there have been a couple of things happening lately that have made people who work on primordial black holes very excited. So primordial black holes and new things related to primordial black holes coming next week. We will do a full 90-minute stream, I believe, about primordial black holes, about the current state of primordial black holes, and how these recent observations affects the state of primordial black holes. It's going to be super fun. I still need to prepare for that. I have to do a lot of reading for it, but it's cool. I love the topic request. So next week, same time as always, there will be a special stream about primordial black holes and the current status of primordial black holes. Then in March, my streaming schedule is going to be a bit erratic because I may have overbooked myself in March. There's at least 2 Sundays for sure in March when I'm not doing 3 Sundays in March when wait, do I have any free Sundays in March? I should have at least 1, right? Maybe 2? Oh God, my March I'm just opening my calendar again and looking at March and being like, oh, mistakes were made. Yeah. Okay. Well, for sure, next Sunday there will be a cup of cosmology because there's going to be the special topic. After that, we'll figure it out. We'll figure it out. Maybe one or two in March. We'll see. But my weekends in March are looking a bit busy. But definitely next Sunday. So next Sunday, same time as I do love press comment. Their current state of primordial black holes, they still suck. They do, but not in the way you think. Tune in next week to learn why primordial black holes are actually very cool. Also, they're very cold. Getting double puns thrown in. Okay, Cup of Cosmology will be back next week, same time as always, with a special topic that is going to be 8 p.m. if you're in Finland, 7 p.m. if you're in mainland Europe, mainland as if we're not connected, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. For any other time zone that I don't know off the top of my head, you can go to cupofcosmology.com where there is a time zone converter so you can figure out when the next Cup of Cosmology is in your own time zone. Alternatively, just make sure you subscribe to the YouTube channel or the Twitch channel because then you can be notified about an hour before or half an hour before I go live. But next Sunday, we're going to plan special topic, special stream. Okay. Thank you everyone for joining today. This has been super fun. I feel like we've had a lot of really cool questions. We've had a lot of tangents. We talked about a lot of really interesting topics. The CMB only appeared like 30 minutes in today. Unbelievable. But then I showed you the beach ball so many times. We need a universal CMB time zone. That does exist. It's the cosmological time zone. Not very relevant for planning meetings though, or planning us, because what is 1 week? What is 1 hour? When you have 13.82 billion years to cover. Might not be overly convenient. Okay. Thank you everyone for joining. It has been great fun. I've really enjoyed all of the questions, all of the topics, all of the random things, all of the tangents we went on. Always super, super fun. Cup of Cosmology will be back next week, same time as always, with a special topic. If you want to request your own topic, go to cupofcosmology.com and follow the instructions. I hope to see you all again next week, same time as always, and I hope in the meantime you will take care of each other and stay curious.